everyone. This is a series of videos that are just a quick introduction to number theory, to some of the basic topics such as divisibility, greatest common divisor, Euclid's algorithm, the Fundamental Theorem of Arithmetic, congruences up to finite fields, going towards a course on cryptography or encryption. So basically the basics that you need for to understand some of the methods in encryption and cryptography. I am actually teaching a course on cryptography in the fall, but I thought I would put these videos on YouTube because other people might find them useful. So let's get right into it. So what is number theory and what do we study? So in number theory, we study, first of all, the natural numbers. So the numbers 1, 2, 3, ... the natural numbers. And of course, we are also interested more generally in the integers. So the integers are the natural numbers, 1, 2, 3, etc., but also the number 0 and also the negative numbers. So these are the integers. And those are, that's the symbol for the integers. And more generally, we're interested in the rational numbers. So the rational numbers are quotients of integers. So quotients of m by n, where m and n are integers. This symbol, if you haven't seen it before, that is belongs to. And we require that the denominator is non-zero. So those are the rational numbers. Now, we usually write fractions in lowest terms. So lowest terms meaning that the numerator and denominator are relatively prime. But we have not defined relatively prime. We have not defined what is the GCD of two numbers. So that's something we're going to do today. Also, I wanted to say that in a full course in number theory, you would define these with axioms, and those axioms would carry some properties that we use to prove theorems about the integers. So these properties, I'm not going to do that in these videos because it's a very quick introduction to number theory. But those properties are, for example, that there is an addition, there's a multiplication for these numbers that have properties such as these operations are commutative, they are associative, and they have a distributive law. And those are essential properties that are used, again, to prove the properties that we know and love of the integers, for example. So I'm not going to go through those, but those are very important for actual formal proofs. So what we're interested in is divisibility, prime numbers, the fundamental theorem of arithmetic. So let's get started with divisibility. So what is, by definition, what is divisibility? So let a and b be integers with b not 0. We say that b divides a, or there's a lot of types of language for this. We're going to write that b divides a using a vertical bar like that in short. But if you want to be more wordy, we say that a is divisible by b, or that b is a divisor of a, or a is a multiple of b if a is b times c for another integer c, for some integer c. Okay, so let me give you some examples of divisibility. So for example, 3 divides 15. Why? Well, by definition, we need to find a number c such that 15 is 3 times c. So in this case, the number 5 works. So again, in the definition, this is c, this is b, and this is a. 15 is divisible by 3. By the way, this also implies the same equation, this equation over here also implies then that 5 divides 15. And also, by the way, 15 divides 15, not because of that equation, but because 15 is 15 times 1. Okay. This definition applies to all the integers, including negative numbers. So we do say that 7 divides minus 21 because minus 21 is 7 times minus 3. So in this case, the value of C is minus 3. And we also say, this definition also applies to 0. We say that 9 divides 0 because 0 is 9 times some integer. What integer? Well, the integer is 0. So 0 times 9 is 0. So this here plays the role of C. This is my role of B, and this is the role of A in the definition. So 9 divides 0, or 0 is divisible by 9. And in fact, 0 is divisible by any number. A divides 0 for all integers A, right? Okay. So let me show you some properties of divisibility that are very useful, that we use all the time. So here's a proposition with some properties. So let A, B, and C be integers. Then first, if A divides B and B divides C, then A divides C. So that means that the property of divisibility is transitive, that if A divides B and B divides C, then A divides C, that we usually call transitivity. B, if A divides B and B divides A, then, well, that is not that A and B are equal, but they have to be plus or minus each other. So one is the either equal or the negative of each other, then that's what happens when A divides B and B divides A. And C, and this is pretty important, if A divides B and A divides C, then A divides B plus C. So whenever you have two numbers that are divisible by one number, their sum is divisible by that number also. Also, their difference is also divisible. In fact, any linear combination in integers of B and C would be divisible by A also. So let me just give you examples of all of this. So example, first of all, 3 divides 15, right? We just saw that. And 15 divides 60, because 15 times, what is it, by 4, that is 60. Then 3 divides 60. And you can see that that is true because 60 is 3 times 20. So yes, that is true. So that's an example of A. For B, well, 7 divides minus 7, and minus 7 divides 7. So they have to be plus or minus of each other, which of course they are. 7 is minus 7, right? And the last one, which, as I said, this is going to be key in what we're going to do in a moment, or in the next video about Euclid's algorithm. If 3 divides 15 and 3 divides 9, then 3 divides the sum of 15 and 9. And that is in fact true because 3 does divide 24, because 24 is 3 times 8, right? So the sum of two numbers that are divisible by 3 is also divisible by 3. Great. So let me actually lasso this proposition, and I'm going to just show you the proof of the third part. Since I said it's important, I'm going to prove it just so you see one proof of how one goes about proving such a thing. So No, so here's the proof of C. Okay, so how do we go about proving such a thing? We're going to, this is an if-then statement. So we can assume this, which we know what that means from the definitions, and then we are going to prove this part. So we can start with suppose A, B, and C are integers in the statement, but A divides B and A divides C. Then by definition of divisibility, there has to be integers. There are integers. I'm going to call them K and H in this case. Oh, that looks like a B. K and H integers, such that, so A divides B means that B is A times an integer, which I'm going to call K, and C is A times an integer, which I'm going to call H. Thus, what am I trying to prove? I'm trying to prove that B plus C is a multiple of A. So I'm trying to write B plus C as A times something. So let's start with B plus C and see what we get. I can substitute B by A times K and C by A times H. And now is where I want to take a common factor of A, but that's where I need what I said, that, well, the integers have a distributive property. And that is key in here, that we do have a distributive law in the integers. So I can write A times K plus H. And now there is one more property of the integers that is key here, and is that the integers are closed under addition. Z is closed under addition, which means that when you add two integers, you get an integer. So that is some integer. I'm going to call it L. So this is A times L. But that where L is an integer. But that means then that B plus C is A times an integer, and therefore A divides B plus C, which is what I wanted to prove, which I'm going to denote with this little box. Okay, so so we have that proof. Now we have divisibility, so we can come up with lists of divisors. So if I have a number, I can come up with all their divisors. But soon we will want to know what is the common divisors of two numbers and what is the greatest common divisor of two numbers. So let's first of all define what is a greatest common divisor. So let A and B be integers. Then the greatest common divisor of A and B, which we are going to denote by GCD of A and B, or sometimes you will see that if from context it's clear, sometimes we will just write AB in between parentheses. So what is the greatest common divisor? Is an integer, a positive integer D, such that, well, two things. It is, just from the definition, it is a common divisor, and it is the greatest of all the common divisors. So first of all, it is a common divisor. This means that D divides A and D divides B, and it is the greatest. How do we express that? If C is another integer, is another positive common divisor of A and B, i.e. C also divides A and C also divides B, then D has to be the greatest of all of this. So D has to be bigger than this one. So this means that D will be bigger than any other common divisor. Okay, so that is the definition. So let me show you what we can do with this. So for example, so let A be 60 and B be 105, and we want to find the GCD of 60. Whoops, that's wrong. Of 60 and 105. So right now we have no tools to do this other than if I have 60, I'm going to write all the divisors of 60. I'm going to write all the divisors of 105, and I'm going to compare, see which ones are common and which one is the greatest. To find all the divisors of 60, I have no tools again. So what I'm going to do is just try to dividing by every number between 1 and 60 and see which ones are divisors. We will see better ways of doing this, of course, to find divisors and to find the greatest common divisor of two numbers. But this is one algorithm, which is a very bad algorithm. So what are the positive divisors of 60? So the positive divisors of 60, I have them all here. They're 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. There are a lot of divisors of 60, which is why 60 was at some point used as a hexadecimal basis, because it's divisible by many small numbers. Great. So, and then what are the divisors of 105? The divisors of 105 are 1, 3, 5, 7, 15, 21, 35, and 105. And again, I found those sort of by brute force, by trying every number between 1 and 60 and see which one divides, which is very time consuming. And we should not be doing that, but we're doing that just here just to show that this is an algorithm, but it's a bad algorithm to do this. So the common ones are 1 is common to both, 2 is not, 3 is common to both, 4 is not, 5 is common to both, and then 15 is common to both. And now you can see of all the common ones, 15 is the largest. So we found it. So the GCD of 60 and 105 is 15. So we have it. But again, this is a pretty bad algorithm. So what can we do? For one, we can accelerate this if we know the prime factorization of 60 and the prime factorization of 105. We can actually find all the divisors a lot quicker, and also we can find the GCD a lot quicker. So prime divisor. So let's see, what is a prime number, first of all. So here is the definition for us. A prime number is a natural number p bigger or equal to 2. I'll mention in a second why we do not want 1 to be a prime, such that it's only divisible by 2 positive divisors, namely 1 and p itself. So it has exactly 2 divisors. Why are these interesting to begin with? Because these numbers that have no other positive divisors other than 1 and itself are the atoms of the integers on their multiplication. So the primes colloquially are the atoms of the integers on their multiplication. In other words, if you want to generate the integers just multiplying a set of basic elements, what you need are the prime numbers. The prime numbers will generate every integer with multiplication it will generate every natural number, and with -1, it will actually generate all the integers, all the non-zero integers on their multiplication. Okay, so what are some prime numbers? So the primes start with 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, etc. Those are the first few prime numbers. And the first very important theorem one proves in number theory, in a course in number theory, which we're not going to do here, and I strongly suggest that you go somewhere and find a proof of the Fundamental Theorem of Arithmetic. And the Fundamental Theorem of Arithmetic tells you that every natural number bigger or equal to 2 has a unique factorization as a product of primes. So every natural number n bigger or equal to 2 has a unique factorization as a product of primes in what format? N is P1 to the E1, P2 to the E2, ER to the ER, where P1 is less than P2 is less than PRR prime. So we order them like this. So the unique factorization is actually just, there's only one way to write them if you write them in increasing order. So these are primes, and the exponents E1, E2 through ER are all integers or natural numbers, let's say, bigger than 1. So by the way, so the key here is actually that the Fundamental Theorem of Arithmetic, there are two things actually stated here. There are two things. It's saying that every natural number has a factorization into primes. That's the first part of the Fundamental Theorem of Arithmetic. And then, very important, it says that that factorization is unique. Now, if 1 was a prime number, this would not be true. 1 would cause problems in that we could write 6 as 2 times 3, but also as 1 times 2 times 3, and also 1 times 1 times 2 times 3, and etc. So that is one reason why 1 shouldn't be considered a prime number, although there are other reasons why we do not consider it prime. Okay, so now let's see what we can do for a GCD knowing prime factorizations. Now, I'm going to assume that I know that 60 is 2 squared times 3 times 5, and that 105 is 3 times 5 times 7. And now I'm going to try to find the GCD. But note that finding factorizations is also something that is very time consuming. So this is not going to be a good method to find a GCD either, but it's a different method. Okay, so by the way, we're going to set up some notation to state what we can do now. We say that P to the E divides N, where N is an integer and P prime and E bigger or equal to 1 if two things happen. If P to the E divides N, so P to the E is a divisor of N, and P to the E plus 1 is not a divisor of N. So this notation means that P to the E is the highest power of P that divides the number N. There is no higher power that does divide. And now what we can state, which I'm not going to prove either, is the following: that we can come up with a formula for the GCD, knowing the factorization of the numbers. So let A, B be integers, then the GCD of AB is it has this factorization for some primes where let me just box this off here, where the QIs are prime and the FIs are bigger or equal to 1, where and the property is that well, each QI divides A and divides B, and so the primes that divide the GCD are those primes that divide both, and they are raised to the largest power that divides both. Okay, so so it is the largest power in QI to the FI divides A, QI to the FI divides B, but QI to the FI plus 1 does not divide A, or QI to the FI plus 1 does not divide B. So the F power is the largest power that divides both A and B, the largest power of Q that divides both A and B, but there is at least one of the two, of A or B, that is not divisible by F plus 1. So it's the largest power of Q that divides both. Okay, so let me show you in the example that we had before. So in the example, I can compute the GCD of 60 and 105 because I know the factorizations of these numbers. This is 2 squared times 3 times 5 and 3 times 5 times 7. And we know then that the GCD is going to be, first, what primes are common to both. 3 and 5 are common to both. And to what powers? Well, 1 is the largest power that divides both, but I can't do 9 because neither 1 is divisible by 9. And 5, also, it has to be to the first power. So they are to the first power, each one of those primes. So the GCD is just 15. Okay. But again, I'll just say, and I'll end this video with this, that this is also very inefficient. This is an inefficient method because factoring natural numbers is, in general, for large numbers, is very expensive. And in fact, it's so expensive that several of the cryptographic methods that I'll discuss later on actually depend on factoring being expensive and factoring being hard in general for a very large number. So instead, use Euclid's algorithm. So that's what we will do next in the next video. So I'm going to stop here. In the next video, we'll do Euclid's algorithm and Bezier's identity.